Get started in a second. All right, sorry for the delay. Let me just open up the chat box. Get some questions. All right, so let's get started. So last time we finished up by talking about amino acids, and now let's talk about how amino acids link together. So when amino acids link together, we get what are known as peptides. Now, essentially, the bond that forms is an amide group. So we know what amides are. We know that for an amide, you have a C double bond O carbon, and attached to the C double bond O carbon, you're going to have a nitrogen. Now, for the amide bond that forms when you link amino acids together, the nitrogen is going to have a hydrogen attached to it, and then essentially it's going to become attached to a carbon group or a carbon, and that carbon would be the central carbon of the next amino acid. So if we were to take a look at an example, draw a dipeptide made from let's say isoleucine, and let's say proline. Okay. So again, the one bit of information that we're going to give you is the side chain. And actually proline, I don't know if proline is the best one to have with the example. Let's do asparagine. So let's do asparagine as the second one. So for isoleucine, the side chain is a CH with a CH3 coming off in one direction, and then a CH2, CH3 going in another direction. And I probably should have given myself a little bit more space. So let's just correct what's here. So CH3 here, and this is our isoleucine, right? And then for our asparagine, the side chain, CH2, connected to C double bond O, connected to NH2, all right? Now, for this particular peptide, we're going to make isoleucine the N-terminal amino acid. And we're going to make asparagine the C-terminal amino acid. So if you remember back into the notes, the way that we define the ends of a peptide, and then eventually, if there's enough peptides together, a protein, is we define the N-terminal end and we define the C-terminal end. The N-terminal amino acid is the amino acid that has the free or unreacted amino group, which essentially, because we're considering the Zwitter ion forms, essentially is going to have the form of NH3+, where asparagine, as the C-terminal amino acid, has the free or unreacted carboxyl group. And what form does that have? That's going to have the form of C double bond O connected to O minus. Now, what makes them free or unreacted? What makes them free or unreacted is that they're not involved in the amide bond or N-amide bond. Because as you'll see in a moment, the way we link amino acids together to form the peptides is from essentially the first amino acid. We're going to take off the O minus from the carboxyl group on the central carbon. And then for the second amino acid, we're going to take off 2 hydrogens from the nitrogen of the amino group attached to the central carbon. So essentially, when you form these amide or peptide bonds, the amino group and the carboxyl group are involved in that. All right. So in this case, what we'll do is let's draw both amino acids in the Zwitter ion form. So we'll start with isoleucine, where we have our central carbon, which is going to be connected to an amino group. In the Zwitter ion form, has the form of NH3 plus, because the nitrogen has 4 bonds and a positive charge. And the carboxyl group has the form of C double bond O connected to O minus. And then we'll have our side chain on the central carbon, which has a CH connected to a CH3 in one direction, and then connected to CH2, CH3 in another direction. So that would be our isoleucine. And because we designated it as the N-terminal amino acid, in this peptide, it would have to be the first amino acid. And we're going to react that with asparagine. So again, off our central carbon, we'll have amino, hydrogen, carboxyl, and then we'll have our side chain, which in this case is CH2, C double bond O, connected to NH2. All right. So how do we link these amino acids together? As we talked about, we're going to go to the first amino acid, and from the first amino acid, we're going to take off the O minus. Then we're going to go of the carboxyl group of the first amino acid. We're going to take off the O minus. Then we're going to go to the amino group attached to the central carbon of the second amino acid. And from that nitrogen, we're going to remove 2 hydrogens. Okay. So essentially, every time you link amino acids together, the byproduct of that is going to be water. And then the bond formation that you're going to get is a bond between the C double bond O carbon of the carboxyl group of the first amino acid to the nitrogen of the amino group on the second amino acid. So when I draw the structure of the product here, I start with my first amino acid, and everything is going to stay the same until I get to that C double bond O carbon. And once I do, I'm going to have my connectivity or my transition from the first amino acid to the second amino acid that's present. So when I take 2 hydrogens off the nitrogen of the amino group on the next amino acid, the NH3 becomes NH. And then that's connected to the next central carbon, which has a hydrogen, CH2, C double bond O, NH2, and then C double bond O connected to O minus. And essentially what you have here, because you have 2 amino acids linked together, would be what is known as a dipeptide. And you notice on the left side, the amino acid isoleucine has the free or unreacted amino group, and the asparagine on the right-hand side over here has the free or unreacted carboxyl group. Okay. Now, We're not going to ask you how to name peptides, but what I want to be clear about is that the name of a peptide is important because the name of a peptide gives the order of amino acids linked together, starting from the N-terminal end to the C-terminal end. Okay. And as you saw in the notes, each amino acid, before you get to the C-terminal end in the name, is going to have a YL ending. And then once you get to the C-terminal amino acid, that's going to just have its full name. Now, the order is so important because if you go back to the example that we just did, when we said talk about draw a dipeptide made from isoleucine and asparagine, this is not the only possibility. The other possibility would have been that I could have made asparagine the N-terminal amino acid and made isoleucine the C-terminal amino acid. And what you would find is if you were to draw that structure, it would not be exactly the same as we drew here. Okay? It wouldn't look exactly the same. So essentially, with these peptides, you have isomerism, where you could have the same peptides present, but the connectivities could be different. And the more and more peptides that you have apart, the more and more amino acids that you have apart as part of a peptide, the more and more combinations are possible. All right. So let's take a look at an example. Draw the structure of, and let me write the name over here, methionine tyrosyl histidine in the Zwitter ion form. Right. Well, let's give you some side chains. Tyrosine. Okay. So the side chain for tyrosine is a CH2 connected to a benzene ring, and then essentially 1, 2, 3, 4 carbons away from the ring carbon where the CH2 is attached to, you have an OH. Now for histidine, the side chain is a CH2, and then connected to the CH2, you have a 5-atom ring that has 2 nitrogens associated with it. And both of those nitrogens have a hydrogen. And the nitrogen that has 4 bonds has a positive charge associated with it. So that's histidine. And then for methionine, for the side chain, you have CH2, CH2, S, CH3. And for this example, the reason why I gave you the side chains in this order is absolutely for a specific reason. And the reason is that I didn't give you them in the order of how we're going to draw the structure. Because again, I really want to reiterate that it's the name that determines the structure in the order that the amino acids are going to be drawn in. Now, as we start to do this, you have essentially 2 options. You can draw all the amino acids separately and then do like we did on the previous slide where we talked about how to put them together. Or if you understand what we talked about there, I'll show you, as I did in the notes as well, how to sort of shortcut it to still come up with the right answer, so to speak. So if I take a look at the name, methionine tyrosyl histidine, what that tells me is that the first amino acid that I need to put as part of this peptide is going to be methionine. Now, since that's the first peptide amino acid that's present, that has to be the N-terminal amino acid. So attached to the central carbon there, I'm going to have NH3+. I'm going to have my hydrogen, and then I'm going to have the side chain for methionine, which is CH2, CH2, S, CH3. Okay. And then I have my carboxyl group. But I realize that if I'm going to link methionine to the next amino acid present in the compound based on the name, what part of that carboxyl group is going to come off? It's going to be the O- off of that carboxyl group that is going to come off. And it's going to be at this point where I have my transition from the first amino acid in the peptide to the second amino acid in the peptide. And we know that whenever we link amino acids together to give a peptide, we're going to get an amide group that has the form of C double bond O connected to NH. Take the oxygen off of the C double bond O carbon of the carboxyl group of the first amino acid. Take 2 hydrogens off the nitrogen of the amino group on the second amino acid. So it's at this point here where I have my transition from the first amino acid in the peptide to the second amino acid in the peptide. Now, based on the name, what is the second amino acid we're going to come across? The second amino acid we're going to come across here is tyrosine, methionine tyrosyl. So tyrosine is going to be the second amino acid that we have present. So this NH is going to be attached to the central carbon of tyrosine, which has a hydrogen attached to it, and then the side chain, which has a CH2 connected to a benzene ring, connected to an OH, and then I get to the C double bond O, the carboxyl group attached to the central carbon of the tyrosine. And then it's from there where I'm going to have my connectivity from tyrosine to the last amino acid that's present in this particular structure. And the last amino acid that's present is, based on the name, is going to be histidine. Okay. So again, I'll have my amide bond that will connect them to each other. So C double bond O connected to NH. Then I have the central carbon of histidine, which has a hydrogen, and then the side chain group CH2, and then the 5-atom ring with the nitrogens. And basically, I'm just copying it like I gave you the side chain on the previous page. And then because this is the final amino acid in the peptide, this is going to be the C-terminal amino acid. So it's going to have the form of the carboxyl group in this case, is going to have the form of C double bond O connected to O-. Okay. And this would be the peptide that you would get in this example. Okay. All right, so that's a little bit about peptides. Now, essentially, when a peptide has 50 or more amino acids linked together, it is classified as a protein. So essentially 50 is the minimum number of amino acids that you have to have linked together for that peptide to finally be classified as a protein. All right. And what we discussed in terms of your proteins are what are known as the levels of protein structure. So let's go through some of the aspects in terms of looking at the different levels of protein structure. Now, essentially, one thing to sort of make note of at the beginning is that most proteins are made up of one polynucleotide strand. Not all of them, but the majority of the proteins that you come across are made up of one polynucleotide strand. And I'm trying to get this eraser to work. Give me trouble. Thank you. Now, the reason why I want to mention this is because the first three levels of protein structure essentially speak of a single polynucleotide strand. Not that it wouldn't apply to a protein that has multiple polynucleotide strands, but in that case, it would refer to them individually, the first three levels of protein structure. And when we say polynucleotide strands, okay, and I'm sorry, don't mean nucleotide, thinking ahead. Wrong term. I'm thinking of chapter 17 on the brain. Okay. So most proteins are made up of one polypeptide strand. We're thinking about your proteins here. So again, the first three levels of protein structure essentially speak of individual polypeptide strands. And in reality, those proteins that only contain one polypeptide strand only really have the first three levels of protein structure. It's only when a protein has multiple polypeptide strands associated with it that you have the fourth level of protein structure. And again, what I was trying to say is that it doesn't mean that if you have a protein that has multiple polypeptide strands, that you don't have the first two levels of protein structure. You would just apply them to each of those polypeptide strands individually. And when we say polypeptide, we mean many amino acids linked together. Okay. And we know for essentially a protein in the polypeptide chains, you have to have 50 or more amino acids linked together. So that absolutely classifies as many. All right. So the first level of protein structure we come across is the primary level. Now, this is pretty straightforward. Essentially, it's the order of amino acids in the polypeptide strand held together by amide bonds. That's all it is. It's the order of amino acids that you have. And again, the reason why the order is so important is because, if you have 50 or more amino acids linked together, and that order sort of lends to what the overall shape and the function of the protein is going to be, if one of those is not in the right order, that's going to be a big problem. So as simple as it might seem, the primary level really is just the order of amino acids in a polypeptide strand held together by amide bonds. Okay. Next, we have the secondary level of protein structure. And what you have here are specific three-dimensional shapes of certain sections of a polypeptide strand. So not the entire polypeptide strand in terms of its three-dimensional shape, but certain sections of that strand that have a specific three-dimensional shape. And the two most common that you talk about are the alpha helix and the beta pleated sheet. Now, the commonality between them is that they both result from hydrogen bonding between amide groups in different parts of the polypeptide chain. You know, as you saw in the notes, if you have a C double bond O group and you have an H, you know, the oxygen of that group is going to have a partial negative charge of the C double bond O group. The hydrogen attached to nitrogen is going to have a partial positive charge. What force of attraction will you have between them? The force of attraction you'll have between them is going to be hydrogen bonding. So both the alpha helix and the beta pleated sheet result from hydrogen bonding between amide groups in different parts of the polypeptide chain. Now, in terms of their shapes, the alpha helix is described as a corkscrew shape. So it sort of spirals around, like if you put a corkscrew into a wine bottle. And in the beta pleated sheet, segments of the polypeptide chain run side by side. Essentially, you have segments of the polypeptide chain that end up running parallel to each other. That's essentially the difference between an alpha helix and a beta pleated sheet. But the commonality between them is that they both result from hydrogen bonding between amide groups in different parts of the polypeptide chain. All right. So the most complex level is the tertiary level. The tertiary level describes the different interactions between the side chain groups in the amino acids present that lend to the overall three-dimensional shape of the polypeptide chain. Now, as you saw in the notes, within that polypeptide chain, you might have certain sections that are alpha helix and other sections that are a beta pleated sheet. But if you look at the picture of a polypeptide chain as a whole, you know, what is that overall three-dimensional shape? Now, usually there's no words to describe accurately what that three-dimensional shape is, because there's so many twists and turns that go along the way. But the reason why you have all those twists and turns, and why whatever shape that polypeptide chain has what it has, is because of the different interactions that you have between the side chain groups in the amino acids present. All right. Now, what I want to do here, I think, would be to do an example. And within the example, we'll talk about some of the different interactions that you have on the tertiary level of protein structure. Okay. So the question here is, identify the type of interaction you would expect between the following pairs of side chains in the tertiary level of protein structure. All right. So in the first example, number one, our first side chain is CH2, C double bond O, NH2. And then the second side chain is CH2, OH. All right. So what do we have going on here? So if I think about the different types of interactions, first off, hydrophobic interactions, which are essentially those van der Waals forces that you have between the side chains of nonpolar amino acids. That's not the case here, because here the side chains are not nonpolar. Both of the side chains are polar. You know, for the first one, you have a carbonyl group, part of an amide. And for the second one, you have OH, alcohol, as part of the structure. So they're definitely not nonpolar. The second one we talked about in the notes is a hydrophilic interaction. Now, that wouldn't be between two side chains. That would be between polar side chains and water, the attraction that those polar side chains would have with water. Now, these two polar side chains individually would have hydrophilic interactions with water, but that wouldn't be between each other. Then we talked about hydrogen bonding. Then we talked about salt bridges. And salt bridges are pretty specific because you only find them between basic and acidic amino acids, when the side chain of the acidic amino acid has the form of C double bond O, O minus for the carboxyl group. And the side chain for the basic amino acid has the nitrogen having 4 bonds and a positive charge. And when that's the case, you can have an ionic bond between them, what is known as a salt bridge. And then we talked about hydrogen bonding, which we know is the attraction between a polarized hydrogen atom in one molecule and a polarized oxygen, nitrogen, or fluorine atom in another molecule. And what you would definitely expect between these two side chains is hydrogen bonding. And really the easiest place to see that is for the first side chain, you have a C double bond O oxygen, which have a partial negative charge. And for the other side chain, you have an OH hydrogen, which has a partial positive charge. What force of attraction are you going to have between them? You're going to have hydrogen bonding. Okay, so that would be the answer to our first example. Second, so suppose we had for the first side chain CH2, C double bond O, O minus. And for the second side chain, we have NH3, wrote that wrong. We have CH2, 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 NH3 plus. All right. So that would be my side chain for the second amino acid here. CH2, CH2, 4 CH2s, and then at the end, NH3 plus. So what do we've got going on here? So if I take a look at the side chain of the first amino acid, it has a carboxyl group as part of its side chain. So what does that tell us? It tells us that this amino acid is acidic. If I look at the second amino acid, the side chain has an amine group as part of the side chain. You know, you have a nitrogen with a carbon group attached to it. So that's an amine group. And that tells us that it is a basic amino acid. And because the oxygen has a negative charge in the acidic amino acid, and the nitrogen has a positive charge in the basic amino acid, that is going to be the main force of attraction between that O- and that N+, the full negative and the full positive. And therefore, you would have an ionic bond, which is known as a salt bridge. Now, let me just show you a difference. Suppose we had the same two side chains, except we were under basic pH conditions. And I just ran out of room on my board to draw. So, or actually, let me move the chat. I can fit it in. So NH3. Okay. Now again, these are still acidic and basic amino acids, but in this case, you can't have a salt bridge. Why is that the case? Well, in the carboxyl group, the oxygen, the single bond oxygen, has a hydrogen attached to it. So it doesn't have a full negative charge. It does have a partial negative charge, but it doesn't have a full negative charge associated with it. And therefore, a salt bridge can occur because you need to have an ionic bond to have a salt bridge. An ionic bond results from ions, no partial charges, full positive, full negative. So what could you have here instead? Well, the nitrogen still has hydrogens attached to it, and those nitrogens are going to have partial positive charges. Again, we can focus on the C double bond O oxygen, which has a partial negative charge. So instead of having a salt bridge between them, you could still have hydrogen bonding. But the key thing here is that the salt bridge essentially would not exist. Okay. Number 3. So for our first side chain, we have CH2SH. And for our second side chain, we have CH2SH. So the last type of interaction that we talked about on the tertiary level of protein structure is what is known as disulfide bonds. And disulfide bonds are very specific because they only result between the side chain groups of 2 cysteines. The side chain for cysteine is CH2 connected to SH, which is exactly what you have here. So essentially, both of these amino acids are cysteine. And therefore, the way that they're going to link to each other is that the sulfurs are going to become singly bonded to each other. And that type of interaction is what is known as a disulfide bond. All right, let's do one more. So here's our first side chain, and here's our second side chain. So what do we have going on here? Both side chains are hydrocarbons. Both side chains are hydrocarbons, okay? So when you have 2 hydrocarbon side chains, the interaction between them are those van der Waals sort of attractions, those essentially dispersion forces, known in this case as hydrophobic interactions. Okay. So you have those dispersion forces that would result, and that essentially would give you your hydrophobic interactions. Okay. All right. So that's a little bit about the tertiary level of protein structure. And then the final level of protein structure is the quaternary level of protein structure. So what do we find on the quaternary level of protein structure? Now, this is the only level that this level doesn't apply again if your protein only has one polypeptide strand, because the quaternary level is a combination of two or more polypeptide strands to form a larger biologically active protein. So again, in order to have this level of protein structure, you essentially have to have two or more polypeptide strands that are present. And one thing to note is that the strands are held together in the quaternary level by your hydrophobic interactions, hydrogen bonding, and salt bridges. So a lot of those interactions that we talk about on the tertiary level of protein structure apply to essentially those to those strands, holding together those strands on the quaternary level of structure as well. You know, hydrophilic, that involves interaction with water. That's not really going to hold the strands together. I guess disulfide bonds, but again, that's very specific. So if you don't have cysteines present, you're not going to have any disulfide bonds that are present as well. So these would really be the three main interactions you would have between the amino acids in the different strands that would hold the polypeptide strands together in the quaternary level of protein structure. One of the things I'm just looking up, because the term van der Waals forces, I think it's more general than what you have in the hydrophobic interaction. So I just want to go back and double check that quick, because I think it's a more general term. Two kinds of van der Waals forces. Weak London dispersion forces. Yeah. So actually, let's go back for a second, because essentially the term van der Waals attractions is a little bit too broad, because for van der Waals attractions, you could have dispersion forces, which I'll mention again and talk about, but you could also have stronger what are known as dipole-dipole forces, which I believe would include hydrogen bonding as well. So I just want to sort of change this. Hydrophobic interactions doesn't change, but essentially what you have there are dispersion forces. So remember, dispersion forces, and we talked about this when we talked about your fatty acids and saturated versus unsaturated. Dispersion forces are weak attractions that exist between things that are nonpolar, where essentially in one molecule you have a shift in electron density that results in a shift of electron density in an adjacent molecule, and then you have essentially ends that become attracted to each other. If something negative is close to another molecule, then in that molecule that's close to that negative charge, it's going to become more positive, and then you're going to have an attraction between them. So essentially, it's what is known as a dispersion force. So I know in the homeworks, I think a bunch of you put van der Waals forces, and I put okay with that. But I want to make it clear that it should be more specific. And really, it's about dispersion forces because van der Waals forces is more of a general term. Dispersion forces is really the more specific and correct term that's here. But to keep it simple, let's just make it hydrophobic interactions and we'll be fine. All right, so that's a little bit about proteins. So the last part of the chapter deals with a discussion of enzymes. So what are enzymes? What's the function of enzymes? Enzymes are catalysts. And what they do is that they make reactions go faster. Okay. I'm not going to go step by step through everything that was discussed in the notes. What I do want to do with enzymes is I want to do a little bit more of problem solving in terms of some of the questions, which I think will lend to a discussion of enzymes in general, instead of me just going sort of verbatim in the notes and such like that. But I'll be brief in these opening comments. So enzymes are catalysts. They make reactions go faster. How do they do this? Well, this occurs when an enzyme substrate complex is formed. And we'll get into that. We'll talk about how the substrate has to become bound to the active site on the enzyme. And when the substrate is bound to the active site on the enzyme, you have an enzyme substrate complex that results. What's the impact of having an enzyme substrate complex? Well, it provides an alternative pathway for the reaction that has a lower activation energy. So what do we talk about when we talk about activation energy? Activation energy is the minimum amount of energy required for a reaction to take place. Sometimes room temperature has enough heat present to get a reaction to occur. Sometimes you have to literally put a flame underneath the reaction mixture to get the reaction to occur. Every reaction requires some amount of energy to be put in order for that reaction to occur. That minimum amount of energy is what is known as the activation energy. The less energy it takes to reach that activation energy, whatever that value is, the faster the reaction is going to occur. Because it takes less to overcome that energy barrier. Essentially, the activation energy is the energy barrier that has to be overcome in order for that reaction to occur. How much energy do you have to put in order for that reaction to actually take place? Sometimes that barrier is just way too high. And therefore, the reaction that you're trying to do may not occur. Usually that's not the case, but that definitely could be the case associated with it. All right. So one of the things that the textbook discusses are the names of enzymes. You don't have to memorize the names of enzymes. I don't really see much value myself in doing that. The biggest thing I would say about the names of enzymes is two things. Well, first, you have to be able to recognize them. And enzymes have names that end in ASE, which is pronounced as A's. So if you see a name that ends in A's, you'll be able to recognize it as an enzyme. And then the other thing that I think is important is that you recognize that the name of an enzyme actually gives you some important information, because it talks about the type of substrate that it will deal with, type of reactant that it will deal with. And it essentially could also describe the type of reaction that it is going to catalyze. I'm not going to expect you to distinguish between the two, whether it's talking about a specific substrate or a type of reaction. But the big thing is that there is definite information in the name of an enzyme and what it's speaking about. So I think it's important to be aware of that. Okay. All right. So let's take a look at an example. All right. So let's take, and this will lead us to discussing some other parts of enzymes. So match the terms with each of the following. The first term is enzyme substrate complex. And that definitely doesn't look like enzyme. The second term is enzyme. And the third term is substrate. With each of the following statements. All right, so here's the first statement. Has a tertiary structure that recognizes the substrate. Okay. So we talked about the fact that an enzyme will only work. It'll only lower the activation energy for a reaction if you can get an enzyme substrate complex to form. Excuse me 1 second. Okay. Now, essentially, molecules are, and you can't see it, but molecules are essentially constantly in motion. When you have enzyme and reactant essentially present, because remember, in a reaction, you're converting reactant into product. The reactant molecules are going to be moving and the enzyme molecules are going to be moving as well. If you think about the idea of binding, the enzyme and the reactant have to become attached to each other. Now, if they're constantly moving, how does this happen? Well, essentially, the enzyme and the reactant have to be able to recognize each other. In other words, they're moving and they see each other, and in one way to think about it in a very simplistic view is that they recognize each other as friends. You're walking down the street and you see your buddy passing by and you stop and say hello. So you're both in motion, you look at each other, you see each other, and you stop and say hello. I kind of like to think about that in terms of enzyme substrate binding. They're both moving, they both see each other, and they recognize each other as friends and they say hello. Now, in the technical sense, what is recognition based on? Recognition is based on shape. But the issue is, not the issue is, but one of the facts is that the overall shape of an enzyme and the overall shape of reactant molecules are not usually very close to each other. And the reason for that is because your reactant molecules, or your enzymes, sorry, tend to be much larger than the reactant molecules. So how do they recognize each other? Well, within the tertiary structure of the enzyme, there is a region known as the active site, whose shape closely matches that of the substrate. And it's within this active site where the substrate, the reactant molecules, and I'll get into substrate term when we come across that answer, it's where the substrate is going to become bound to the enzyme. And that's going to give you the enzyme substrate complex. So the answer to this question, of course, is 2, enzyme. Letter B. Letter B says the combination of an enzyme with a substrate. And we've essentially talked about this. That, of course, is an enzyme substrate complex. And then letter C has a structure that fits the active site of the enzyme. And that, of course, would be the substrate. Let's talk a little bit more about substrate. So in terms of the we talked about how, you have reactant molecules and you have enzyme molecules that are present and they're going to be in motion. Well, one of the questions is how many reactant molecules and how many enzyme molecules do you have? Well, one of the ways to talk about that would be is if you have, let's say, what is known as 1 mole of a reactant, and if it's, let's say the reactant is a covalent compound, that means you're going to have 6.02 times 10 to the 23rd molecules of that compound. Now, that's a lot of molecules. What an enzyme is going to do is that an enzyme is not going to work with every single reactant molecule at once. Essentially, depending on the amount of enzyme that you have, there's usually only a singular region, the active site, where that essentially that the reactant molecule is going to fit into. Essentially, those reactant molecules that bind to the active site, they are what are known as substrate. So those are the ones that, in a sense, at a certain time, are going to become bound to the active site on the enzyme. And that gives you an enzyme substrate complex. And then once that substrate is converted into product, then it's released from the active site. And now that active site can bind with a new batch of reactant molecules, or the enzymes that are present, could be, or the molecules of enzymes that are present, could react with a new batch of substrate molecules. And in reality, every single reactant molecule is not attached to enzymes at the same time. There's a portion of them that become attached to the enzyme molecules. And if you think about it, an enzyme molecule having 1 active site per molecule, and I don't know if there could be more per molecule. I'm not 100% sure, but essentially, the small group of reactant molecules that get converted to product at a time, that small group is what is known as substrate. So basically, your substrate is the same as reactant, but the substrate would be a small group of those reactant molecules. That's sort of the difference between them. Substrates converted to product with a lower activation energy, and then the product is released from the active site. And when you have that attachment, we call it an enzyme substrate complex. All right. So that was one example I wanted to take a look at. Let's take a look at trying to see another example. This one we did in the homework, I think. All right, so let me just talk quickly about some models of enzyme substrate binding. Okay, so one of the key things to understand is that not every enzyme will catalyze every reaction. For the most part, we describe enzymes as being specific. In a very simple term, an enzyme should only work with a specific reactant, specific substrate, so to speak. It's a little bit broader than that, not too much. If you have an enzyme that catalyzes a certain reaction, it might work with different reactants that fall into that reaction. But usually it's not a broad range of specificity. Now, in terms of how close in shape, well, essentially, we talked about how, the enzyme, the active site on the enzyme, and it's going to be the active site on the enzyme and the shape of the substrate molecules that are going to be similar in shape in order for recognition to occur. So the shape of the substrate and the shape of the active site on the enzyme have to be similar in order for recognition to occur. Then the question becomes, how close in shape? The earlier model to speak about this was what is known as the lock and key model. Essentially, the lock and key model describes the active site as having a rigid, non-flexible shape. And therefore, in order for binding to occur, the shape of the substrate, the shape of the reactant molecules, the shape of the substrate, would have to have an exact match to the shape of the active site. Just like how, and I know, now you have these push button locks and all that other stuff, but, you think about a key going into a lock, there might be more than one key that fits into that lock, but there's only that exact match for that cylinder that's actually going to turn the lock and open what you're trying to get into. If the key to my house, you might have a key that fits into that lock, but it better not, or it should not, turn that lock to open the door to my house. I should have the only key that not only fits into that lock, but turns the lock and opens the door. And that would be because that key has basically an exact match to the cylinder inside the lock that turns it. In early days, it was really thought that the shape of the substrate molecules and the shape of the enzyme molecules would have to be that close in order for enzyme substrate binding to occur. But what they found is that enzyme substrate binding was a little more flexible than this. They were seeing instances where the shape of the substrate molecules were not necessarily an exact match for that of the enzyme, the active site on the enzyme, but yet the enzyme was still working. And therefore, essentially, the more accurate model is what is known as the induced fit model of enzyme substrate binding. What the induced fit model sort of states to is that essentially the active site can slightly adjust its shape to better fit or to better bind the substrate. Now, slightly adjust because wholesale changes in shape are not going to occur. But the active site can make slight adjustments so that the substrate can really fit nice and snug into the active site. Now, in the lock and key model, the active site would make no adjustment at all. And basically, if that substrate was not going to fit exactly in, the substrate was not going to fit. But it wasn't as rigid as that. And it was found that the active sites slightly adjust their shapes to better fit that of the substrate. So essentially, by doing so, they are, quote unquote, inducing a fit. And this is really the more accurate model of enzyme substrate binding, that it doesn't have to be an exact match, but it better be close, because the active site will slightly adjust its shape to better fit that of the substrate, but wholesale changes in shape are not going to occur. All right. Last thing to talk about with enzymes are factors that affect enzyme activity. And I still have been never able to figure out the difference between affect and effect. Factors that affect enzyme activity. What do we talk about when we talk about enzyme activity? Essentially, we're talking about how well an enzyme is working. Just because you add an enzyme and you would expect it to catalyze the reaction of that particular substrate doesn't mean it's always going to do that. Because essentially, enzymes and how well they work are affected by reaction conditions. The two main ones are temperature and pH. Okay, temperature and pH. So to speak about this, let's take a look at an example. So we've got trypsin and I won't give you the whole definition of what it is, functions in the small intestine at an optimum pH of 7.7 to 8.0. How is the rate of a trypsin catalyzed reaction affected by the following conditions. Okay. And the first one would be running the reaction at 75 degrees Celsius. Okay. So essentially, letter A speaks to temperature. Okay. So we talked about the fact that enzyme and substrate molecules are constantly moving. At different temperatures, they are going to be moving at different rates because temperature is a measure of heat that is present. Heat, of course, is the main form of what? Heat, of course, is the main form of energy. Okay. Heat, of course, is the main form of energy. And the energy that's present is going to impact how quickly the molecules are moving. At very low temperatures, molecules are not going to be moving. They're going to be very stagnant. So if the enzyme and substrate molecules are not moving, they're not bumping into each other as they're walking down the street. They're not walking down the street, they're staying still. So they stay far enough away that they don't recognize each other. So even though you have enzyme present, how well is the enzyme working? The enzyme is going to not be working very well. Now, as you start to go up from low temperatures, that means that you're increasing the amount of heat that's present in the system. What that's going to do is that's going to provide more energy, and that's going to cause both enzyme and substrate molecules to pick up their movement. So what happens when they pick up their movement? What happens when they pick up their movement is that they're going to move faster. And that means that more interactions are going to occur. They're going to recognize each other a lot. There's going to be a lot more recognition occurring. So what does that mean about how well the enzyme is working? Now the enzyme is going to be working much better because now you're going to see the reaction rate. And when we talk about reaction rate, we talk about how fast a reaction is going. The less energy it takes for a reaction to occur, the reaction can occur faster. That's why enzymes speed up a reaction, because they lower the activation energy, and that makes the reaction occur faster. However, there will be a certain temperature where the enzyme will be working at its best. And once you go past that temperature, now the way the enzyme works will actually not be as good. And that temperature is what is known as optimum temperature. And for most enzymes, optimum temperature is 37 degrees Celsius. And what's the impact of that? The impact of that is that, of course, is body temperature. So our bodies are set up to have most enzymes work at their best. And that's a great thing because most reactions at 37 degrees Celsius do not occur very quickly. And in reality, in order for us to sustain life, the chemical reactions that take place in our body have to occur at very fast rates, where 37 degrees Celsius usually doesn't support that. Now, once you go past the optimum temperature, the enzyme activity is going to be less and less, because what starts to happen is that essentially the three-dimensional shape of the enzyme starts to become distorted. And eventually, if you heat the enzyme too much, what happens to it? It becomes denatured. And remember, denaturation essentially is the destruction of the three-dimensional shape of the enzyme, with something happening to the secondary, tertiary, or quaternary levels. And therefore, the enzyme can no longer function as it should, because it doesn't have its three-dimensional shape, And now the shape of the active site is no longer what it should be. So in this case, we can make the assumption, because trypsin is in the small intestine, that the optimum temperature is 37 degrees Celsius. So if we jack that up to 75 degrees Celsius, what essentially is going to happen to the reaction rate? The rate will decrease. Okay. The rate will decrease, because essentially the assumption would be that we are starting the reaction at 37 degrees Celsius. If we jack the temperature up to 75 degrees Celsius, maybe not so much to say the rate will, how is the rate of a trypsin catalyzed reaction affected by the following conditions? I don't know if rate will decrease is the best answer. I want to say the rate would be as if the trypsin wasn't even present. I mean, I guess they should, I mean, and I say that because they didn't give you a starting temperature, you know, so, I mean, if you put rate is decrease, I'd be okay with that. Because I would be okay with the assumption that starting temperature was 37, but they say in the question running the reaction at 75. So to me, the most appropriate answer would be the rate would be as if the trypsin wasn't even present. Because basically at that temperature, the trypsin should be denatured. And hopefully by the time we're done, I'll know how to spell trypsin. All right, so that's letter A. All right, letter B. Changing the pH to 3.0. So in this case, we can assume we are at optimum pH to start, because they use the word changing here. Okay. So let's talk about pH. So just like every enzyme has a temperature where they work at their best, every enzyme has a pH where they work at their best. And that pH is 7.4. Sorry, that pH is what is known as optimum pH. Now, for most enzymes, optimum pH is right around 7.4. And what's the significance of that? That pH is physiological pH. In other words, that essentially is the pH environment of our bodies. So the good news is not only are our bodies set up temperature-wise to have most enzymes work at their best, our bodies are set up pH-wise to have most enzymes work at their best. What does the optimum pH do? The optimum pH is the pH that best maintains the tertiary structure of the enzyme. And the reason why doing that is so important is because you want to maintain that tertiary structure, or the shape of that, to maintain the shape of the active site. Now, as you go above or below the optimum pH, the shape of the tertiary structure is going to start to be affected. You know, what type of interaction on a tertiary structure is greatly impacted by pH? Salt bridges. You know, salt bridges are very pH dependent, and you can go back to our discussion of acidic and basic amino acids and how we talked about the difference between those amino acids at physiological pH versus the isoelectric point. Salt bridges are very pH dependent. If you have a salt bridge where changing the pH disrupts that, that's going to impact the tertiary, the the shape of the enzyme. It's going to impact the tertiary structure. Now, if you go too acidic or too basic, you might reach a point of no return, and that would result in denaturation. So the enzyme would no longer function as it should. So in this particular case, if we start at a pH of 7.4 and we change the pH to 3, what should happen to the rate? The rate will absolutely decrease. Okay. If we were given a scenario where we were told for trypsin, just to go back to the question itself, for trypsin, the optimum pH was 7.7 to 8. So again, for most enzymes, optimum pH is around 7.4, but in either case, the rate would decrease here. If we were given a scenario where we talked about changing the pH from, let's say, 6 to 7.5, well, that would have the opposite effect. That would actually make the rate increase, because now you're getting more towards back what the actual three-dimensional, the actual shape of the tertiary structure should be. All right. All right. One more thing for this evening. So the last thing in terms of affecting the way an enzyme works is inhibition. Okay. There are different types of inhibition, but when inhibition occurs, the substrate cannot bind to the active site on the enzyme. Okay. There's three types. The two main types are competitive and non-competitive. So let's take a look at some examples. Let's take a look at an example to have this discussion. So indicate whether each of the following describes competitive or non-competitive inhibition. All right. So letter A says the inhibitor has a structure similar to that of the substrate. Okay. Competitive inhibition, it's a race between the substrate molecules and the inhibitor molecules to get to the active site, because the shape of the substrate molecules and the shape of the inhibitor molecules are close enough to each other that the active site recognizes both. Now, if the substrate gets to the active site first, perfect. Reaction's catalyzed, you get the enzyme substrate complex. But if the inhibitor gets to the active site first, now we got a problem, because the substrate can't get in. And if the substrate can't bind to the active site, you don't have the enzyme substrate complex. So what you have here describes an aspect of competitive inhibition. Okay. Letter B. The effect of the inhibitor cannot be reversed by adding substrate. Okay. So in non-competitive inhibition, the shape of the substrate molecules and the shape of the inhibitor molecules are not that's similar to each other. They're different. So the substrate is going to be recognized by the active site on the enzyme, but the inhibitor is not. But what this inhibitor does is that it attaches to another portion of the enzyme. And when it attaches to another portion of the enzyme, the shape of the enzyme becomes distorted. And if the shape of the enzyme is going to become distorted, what's going to become distorted as well? The shape of the active site. So now when the substrate goes to fit into the active site, it can't. If that inhibitor is attached to the enzyme and the shape of the active site is distorted, you could add substrate all day long. That substrate is not going to be able to bind to the active site on the enzyme. And therefore, this statement here is reflective of non-competitive inhibition. Letter C. The inhibitor competes with the substrate for the active site. It's a race, it competes. And in order for them to compete with each other, their structures have to be similar. And therefore, this describes competitive inhibition. Letter D, the structure of the substrate the structure of the inhibitor is not similar to the substrate. And we talked about this type of inhibition. Being, and of course now we're almost done and we're gonna run into a nightmare. What's going on? Let's try to fix what's going on. All right. Is not similar to the substrate. We describe this as being non-competitive. Because in this case, the active site recognizes the substrate, it doesn't recognize the inhibitor. So it's not a race, it's not a competition. So it's non-competitive. And then finally, letter E, the addition of more substrate reverses the inhibition. Now, when we talked about non-competitive inhibition, we said that if the inhibitor is bound to the enzyme, the shape of the enzyme is going to become distorted. And you could add substrate all day long. That substrate is not going to become attached to the active site. Now, you could add a chemical reagent that has the potential of removing the inhibitor from the enzyme. And the enzyme could go back to its original shape. That's with non-competitive. With competitive, because it's a race, one of the ways we can tilt the favor of getting the substrate to the active site before the inhibitor does is by adding more substrate. Because with all else being equal, if you have more substrate than inhibitor, what are the odds of the substrate getting to the active site first? It's better. If you have equal amounts and all things are equal, you have a 50-50 chance of one getting to the active site versus the other. But if you double or triple the amount of substrate as compared to inhibitor, and if all of the things are equal, there's a greater probability that the substrate is going to get to the active site first. And therefore, this describes competitive inhibition. Okay. And then just to briefly mention, the other type of inhibition is what is known as irreversible inhibition. The main difference is that irreversible inhibition can't be reversed, because what happens is that the inhibitor forms a covalent bond, an actual covalent bond, to the within the active site of the enzyme. Here you're going to have, when inhibitors attach to the active site, or the inhibitor attaches to the enzyme, you're going to have things like hydrogen bonding, salt bridges, intermolecular forces like that. Covalent bonds, single covalent bonds, are not easily broken. So if an inhibitor is going to form a single bond within the active, a true single bond within the active site of the enzyme, the inhibitor ain't going anywhere. And if the inhibitor ain't going anywhere, the enzyme is basically done for. And that type of inhibition would be irreversible. All right. So that's really all about enzymes and such like that. So that brings us to the end of our session for tonight. So if you're able to join me Saturday morning, we'll do some problems from chapter 17, nucleic acids, to get you all ready for the exam on Tuesday. All right. Chapter 17 homework is due. I will try to grade that as quickly as possible to get that back to you as quickly as possible. But on Saturday morning, we'll do nucleic acids and protein synthesis. And of course, if you can't join, I'll be recording the session to post to Canvas. All right. Any questions before we say goodnight for tonight? All right.
Question, sorry. We have to let you know when we can take the test for next week, this weekend, right?
Yes. So I'll be posting that announcement shortly, but same as before. Yeah. So if there's time issues again, let me know. Just remind me, of course. But yeah, the time would be this weekend to talk about when you're going to take the exam. Yes.
Okay. Thank you.
You're welcome. Any other questions? All right. Stay well, and hopefully we'll see you on Saturday morning.
Thank you.
Have a good one.
Take care.
Take care. Have a good night.